Test for divergence. Let's take some infinite series and prove divergence using test for divergence. This test is telling me that if the limit at infinity of the sequence a sub n does not exist, or is different than 0, then the series is divergent. Let's see. Determine whether the series converges or diverges. State any test you are using. The summation from 1 to infinity n over n plus 1. I will try to use test for divergence first. Limit of n over n plus 1 at infinity. We can see n in the denominator, n also in the numerator, the same degree, leading coefficients 1, the ratio of the leading coefficient also 1. That means this limit at infinity is simply 1. It's different than 0. Then I can conclude that my infinite series is divergent by test for divergence. We can try to just to prove it numerically. I will expand this summation. The first term is 1 over 2 plus, because that's what sigma is telling me to do, add, and then 2 over 3 plus 3 over 4 plus 4 over 5, and then I can keep working. But what I know that the behavior of this expression at infinity, it's almost 1. This means that I will be keep adding almost 1 at infinity. And of course, 1 is the finite number. Adding 1 infinitely many times, I am creating a huge number. I can say infinity, or I can simply say this sum doesn't exist as a finite number. It's just a huge number, infinity, which we call divergence, right? Because we know that if it's infinity. That means this is the reason that if this limit exists as a finite number, in this case, the limit is different than 0, that's these ones. Yeah? We can say that the sequence is convergent to 1, but this is not helping me with the convergence of the series. The series is divergent. Example number 2. The same thing. Let's take this series and check converges or diverges. I will find a limit right away, which means I'm trying to apply the test for divergence. -1 to the n plus 1. So now I do have the alternating one. Because of that part, I have alternating series. If n is odd, then it's -1. If n is even, I have positive term, +1. That's mean what I will do. One of the property to find this limit, I can take the absolute value. But let me write down first the property. If the limit of the absolute value of the sequence equals to 0, then the limit of the original one, it's also 0. And that means this is quite helpful, especially if a sub n includes -1 to the n, which is the alternating one. Because taking absolute value, I'm simplifying. The thing is, I'm only looking for 0. Because if this limit is not 0, then the original one most likely is undefined. The limit is undefined. Let's see. Taking absolute value, my sequence will change just n over n plus 1, because -1 to the n becomes always positive. And this limit is 1. That means this limit is also different than 0. Now I'm using this property. If this limit is different than 0, then I can't assume that my original sequence is 0. I can only say this. Let's copy one more time the sequence, -1 to the n plus 1, and we know that this part is 1. Not having this absolute value, I also know that this will give me the value positive or negative 1. That means theoretically the limit doesn't exist as a finite number, as a one finite number. It's simply positive 1, negative 1, positive 1, negative 1. The terms like alternate. And I can say this limit doesn't exist. We're not even writing this way, right? But that's the thing. I can't say the limit is 1. The limit doesn't exist. That means since the limit doesn't exist, I can conclude this infinite series is divergent by test for divergence because the limit doesn't exist. Let's look another one. Again, the summation from 1 to infinity n squared over 2n squared plus 5. We can see right away that computing the limit n squared over 2n squared plus 5 as n goes to the infinity, we have 1n squared and 2n squared, the same degree of the function. I can take the ratio of the leading coefficient. The limit is 1/2. Limit is different than 0, then the infinite summation of a sub n, we know what is a sub n, the infinite series is divergent. And maybe one more time I can expand. 1, 2 plus 5 is 7, and then if I will put 2 I will have 4. 4 times 2 is 8 plus 5 is 13. That means I can of course keep working, but what's happened at infinity, almost all of the terms are approaching 1/2. Of course I will create a huge number. This is giving me divergence, not even a chance for convergence. If the limit is 0, then we can think what to do. But if the limit is different than 0, the infinite series is divergent. I can say that the sequence is convergent to 1/2, but not the summation of infinitely many 1/2s. Example number 4. Okay, the same thing, but the alternating one. We know what to do. Limit at infinity of negative 1 to the n, n squared, 2n squared plus 5. We know that if we have this alternating part, I may try to use this. I will take the absolute value. Taking an absolute value, my sequence changed for now, just n squared, 2n squared plus 5. Because these terms are positive, absolute value of the positive number is positive number, but this one, sometimes is positive 1, sometimes is negative 1, will change for positive 1. And we know that this limit is 1/2. That means this limit is different than 0. Then I can say that the limit of the original sequence, negative 1 to the n, n squared, 2n squared plus 5, the same thing. Like the previous problem, this part is giving me 1/2, but this part is giving me positive negative 1. That means I can't really say positive 1/2, negative 1/2, positive 1/2, negative 1/2. Yeah, that means this limit doesn't exist as a finite number. It's simply undefined. If the limit is undefined, the infinite series is divergent by test for divergence. Okay, let's look at the other one. Let's do the same. I know my tool, test for divergence. Let's apply right away. Limit as n goes to the infinity, n plus 4. Or actually, I can speed up a little bit. Maybe I can distribute. Distributing n, I will have n squared plus 4n, and then expanding denominator, I will have 4n squared, and then minus 2n and 2n will be 4n plus 1, as if we will FOIL this. And then I can nicely see the leading function is n squared, 1n squared, and 4n squared. The limit is simply 1/4. The same thing, different than 0, this infinite sum is divergent by, I can use the shortcut, test for divergence. That means please remember, because this finite number always is giving us like we can misinterpret because we will think that this is actually convergent. The sequence is convergent, but adding infinitely many 1/4, it's not helpful for convergence. It's simply giving me divergence. Example number 6, the same thing. Let's try to jump to the limit right away. Check how the sequence ln of n squared plus 1 over 3n squared plus 1 behaves at infinity. The natural logarithmic function is continuous function. That means I can just compute a limit of the inside function, and we can see the ratio of polynomials n, 1n squared, 3n squared, 1/3. That means the final answer is ln of 1/3. I can leave it like that. It's a finite number different than 0. As soon as it's different than 0, the infinite series is divergent by test for divergence. Because the limit of the sequence is finite number. One more time, the sequence is convergent, okay, to ln of 1/3, but not the series, because then I have to keep adding ln of 1/3, ln of 1/3, and I will create a huge number. That means the sequence is convergent to ln of 1/3, not the series. Series is divergent. Okay, example number 7. Determine whether this infinite series, inverse tangent of n, is convergent or divergent. Let's investigate the behavior at infinity of this expression, inverse tangent at infinity. We all know that this is pi over 2, different than 0. That means expanding this, I will have inverse tangent of 1 plus inverse tangent of 2 plus inverse tangent of 3 and so on. But at some point, the values will be so close to pi over 2, pi over 2, pi over 2. Of course, this is divergence. The infinite series inverse tangent of n is divergent by test for divergence, starting from 1 and infinity. We can even plot this. Okay, I can actually say a sub n, and we know that inverse tangent behaves like that, but since we are talking about just the sequence, we will only have the discrete values. Inverse tangent of 1, inverse tangent of 2, inverse tangent of 3, inverse tangent of 4, and so on. And we know that bounds. This yellow line, it's not gonna be greater than pi over 2. We of course not talking about the negatives. Okay? We only looking at these values. They are approaching pi over 2, we can see, but not getting greater. That's the limit. And this is why my infinite series is divergent, because the limit exists as a finite number. Example number 8. Let's compute a limit, how this expression behaves at infinity, e to the n over n to the power of 5. And we know that exponential function grows much faster than power function. Then if the numerator is winning, it's always infinity. That means this limit is infinity, or I can say this limit doesn't exist as a finite number. Infinite series is divergent by test for divergence. Okay? And that's the proof. Or doesn't exist. Excellent. Example number 9. Another limit to investigate limit as n goes to the infinity, n over natural log of n. We also know that function, the power function, is much, much faster than logarithmic function. Logarithmic function is one of the smallest one. If the numerator is winning again, infinity. Or I can say the limit doesn't exist as a finite number. This infinite series is divergent. By test for divergence. Why is divergent? Because the limit doesn't exist. Okay, because we can imagine these terms n over ln of n, it's like huge infinity, and then sigma is telling me to add, like, of course that's infinity plus infinity plus infinity plus infinity. Am I getting somewhere? Of course not. I'm getting just a big huge number, divergence. Example number 10. We remember, okay, this limit, I hope. Let's write limit as n goes to the infinity, 1 minus 3 over n to the power of 6 over n. I will not prove this because if you watch my videos about the sequences, I did prove this limit, and I can write down maybe here limit as n goes to the infinity of 1 plus a over n b times n. Okay, that means this is a and that's b. That's not 6. Then this limit is equals to e to the power of that quantity a and that quantity b. Please make sure that you know this limit, or even simple, more simpler, 1 plus 1 over n to the power of n, it's simply e. That means that's actually the original one. But as soon as I put extra coefficient here and extra coefficient here, that's how the value e will be affected. The exponent will be a times b. And what we see? We see the quantity e to the power of negative 3 times 6. That means this limit is e to the negative 18. Of course, weird number, I can possibly write like that, 1 over e to the positive 18, but this is definitely a finite number different than 0. This infinite series is divergent. Divergent by test for divergence. And why is divergent? Because the limit of the sequence, it's a finite number. Okay? The sequence is convergent. Yeah, I can say the sequence converges to that number, but not the series. Okay? Series is divergent. Because of that finite number, you have to imagine that series means the sigma, addition. We will be adding and adding and adding all of these numbers. Huge divergence. Example number 11. Let's find a limit. It's the summation from 1 to infinity, 1 over n. 1 over n. Oh, actually, 1 over big number is 0. That's weird. The limit is 0. That means, please remember, we can't use the test for divergence. It's not applicable. If the limit is 0, theoretically at this moment we know nothing about the convergence or divergence. We have to look for different tool for different tests, which I will introduce in my next videos. Okay? Because this is the first test. That means, please remember, if the limit is 0, we know nothing. But however, if we look closer to our formula, we probably recognize that this is really one specific infinite series. Is the harmonic one. Harmonic series. Let me put this somewhere. test for divergence not applicable. But this is harmonic series, and we know that the harmonic one was also proven in my previous video. Harmonic series is always divergent. That's what we can say, but please remember, I'm only saying because of the harmonic. I know the name, I know the property, I know convergence, in this case divergence. I'm not saying that this infinite series 1 over n is divergent because limit is 0. No, if limit is 0, please remember, we know nothing about the convergence and divergence, and we can't apply test for divergence. Okay, I know that is divergent because it's the harmonic one. And let's look at one more. Summation of sine of n over n. Let's check how this behaves at infinity. Sine of n over n. That means what we can do for this one, we can try maybe to use the squeeze theorem. We can use it. The maximum value of sine is 1, and I will keep the denominator. The minimum value for sine of n angle is -1. And as n goes to the infinity, 1 over big number is 0. Of course, as n goes to the infinity. And -1 over big number is also 0. As n goes to infinity. That means if this is 0 and this is 0, the same limit, the middle part is also 0. Okay, by the squeeze theorem. Or we can say it's really informal. I can say that sine of n at infinity, we know how function sine behaves, +1, -1, right? That means I can say positive, -1, but this is n. That means +1 over infinity or -1 over infinity over a big number will also give me 0. But I will remove that and I will put 0 right away. This is more proper way to solve this limit because we're using the squeeze theorem. Okay, that means this limit is 0, and again I can't use test for divergence. Unfortunately, is not really helpful. I don't want to say useless because it's really useful. We just saw for the first 10 problems. And what we need, this one, sine of n over n, doesn't look like the harmonic one. I don't know what to do. I think I have problem. That means I don't know if it's convergent or divergent. Please check my next video.